So on that note, we can also define a notion of convergence in complex plane just by using the norm that we defined in the first video. So now we will move forward and look into a theorem that says that C is complete. We won't prove it. It's quite trivial and left as an exercise for you. So now we will look into some topological considerations. So suppose that Z naught is a complex number, then a disk is defined as d of r at Z naught is equal to the complex number Z such that the modulus of Z and Z naught is less than r. So this is what we mean by an open disk, and by closed disk we just include the boundary points. So yeah, this is what we mean by the disks. So now we'll define an important object that will help us in defining many other things, which is diameter of a set. So say omega is an subset of complex numbers, then take a set A such that that equals modulus of Z minus W such that Z and W both belong to uh, omega. So the supremum of A is defined as the diameter of A. Now, why this exists is a question of its own, and I leave this as an exercise for you to prove. So, yeah, the next definition says that a set is compact if it is closed and bounded. Now, there are many alternate definitions of compactness that take into account more general structures, but since C has a vector space structure, this is equivalent of that, so we might not worry about this. This is a pretty sufficient definition for our study. So the next proposition says that suppose we have a sequence of compact sets that are like this. Then we claim that, and yeah, also the limit as n approaches infinity, the diameter of omega n is equal to 0. So the compact sets are getting smaller and smaller as we move as larger n's. So yeah, we claim that this set collapses to a particular point. So we say that there exists a unique W belongs to C such that W belongs to omega n for all n in natural numbers. So yeah, we will prove this theorem. So since omega n is non-empty, we can say that let belongs to omega n, then Zn defines a Cauchy sequence. And why is that? That is because of the since the diameter of omega n is approaching zero, so we can get our sequence points as closer to them as possible. So yeah, this follows from that. You can formalize this as any way you want. So yeah, Zn defines a Cauchy sequence, and since C is complete, the following sequence is convergent. And hence, since it is convergent, there exists a limit. So let Z not be the limit. So note that Z naught belongs to omega n for all n in natural numbers. And why is that? That is because of the following relation. Since omega n belongs to, I mean, Zn belongs to omega n, and since Z naught is closer to omega n, so yeah, we can argue this. So now we will prove the uniqueness of this Z naught. So if there exists such that then will be always greater than, which is greater than 1, which is a contradiction. Hence we have proved the existence and the uniqueness of the following point. The only thing that is left is that why does omega naught belongs to, I mean, Z naught belongs to omega n for all n? I think you can argue this by yourself, and yeah, you can just do some first order logic and get your answer. So now we will define one of the most important concepts, that is the concept of connectedness. So if omega is an subset of C, then it is called connected if there exists no subsets of say u and v which are subset of omega and their intersection is phi such that u union v equals omega. So we are just saying that a set is connected if there exists no disjoint subset of that set that when added gives you the set back. So this is what we mean by a connected set. And note that a connected open set in C is called a region. So yeah, we are pretty much done to do